let's get started. Right, so yesterday we started to talk about the impact as an application of the conservation of linear momentum, and the equation was like V1 plus the integration from T1 to T2, the sum of all the forces acting on the body integrated with respect to time, and this will be equal to mv2. And we represented this by, like here, this is my particle. And you have a certain momentum acting on the particle like this. You have mv1, and you have like a force over the time acting in this way, and you will end up with having a momentum like in this direction, mv2. And we talked about the impact, like you have two particles colliding together. We talked about the phases of the collision, how it starts, how the particle approach each other. So let's see here. So if you have particle A and particle B, and particle A is moving towards particle B, and knowing that the velocity of A is more than B, first they will collide together and they will be like a one body. And actually this phase, we call it a deformation impulse. Like imagine two soccer balls hitting each other together, so some deformation will happen between them. And at the time, like just after the collision and during the collision, so the time in just after before the collision is called the formational impulse, and the forces acting on the bodies is B, and then they move as a one body for just like a very little moment, like less than a second, and then they will go away from each other, and we call this phase as the restitutional impulse. And finally there will be two separate bodies, like as we can see here, and some of the momentum goes from the high momentum body to the low momentum body, so you will end up with that VB2 is more than VA2. So the first phase, VA has the velocity of body A is more than B, but after the collision, B take the momentum from A and be having more velocity than A. And this is called a linear impact or a central impact, like both bodies on the same line, the velocity vector coincide with the velocity vector of the other body. And today we will talk about the oblique impact, where you have two bodies. Like let's assume that we have this the x-axis, and let's assume that this is y-axis. And actually let's assume this is a table, and you have two marbles, like a billiard table or a ping pong table or whatever. So this is like a table, and you have marble A here, and you have marble P here. And all of them is moving this way towards the here, like this, and this is moving like that, and they came together to collide at this location. And after the collision, each one of these goes in different direction. Like this A came here, and this is A, and this is B. So the line of impact that each one of these bodies affect by forces on each other is this one. So we don't have forces this way. So there's not any forces acting in this way. So the forces that we have, body A acting by a force, like let's assume that this is the deformational impulse, and this is the impulse B, dt, and it's in negative direction because it's going down. And body B acting by impulse force on body A in this direction. So, and it's in positive direction, B dt. So we only have impulse in one direction, and we call this direction is the line of impact. So this y is called the line of impact, and the x-axis is called the line of contact. So first you will have to identify the line of contact like this, and the line of impact is perpendicular to the line of contact. So the line of contact where these two bodies touching each other here, and the line of impact is the perpendicular one, and we only have impulse in the direction of the line of impact. So right now let's separate these bodies and see what is the momentum and the impulse that each body have. So we will have here body A and A. So this is body A, and let's solve this in x and y axis. So let's have the momentum and impulses in x and y axis. So we know that A is moving this way. So here's mVA1, and after the impulse, it moves this way with mVA2. Sorry. After the impulse, it will go this way because we are in the same body right now, which is body A, mVA2. And body B goes this way with mVB1, and once it collides with body A, it will have a reaction this way, mVB2. So this is the vectors and this is the directions, and right now we need to solve this in x and y direction. So for body A, you will have, if you get the components of the velocity, you will have mVA1x, and you will have like this mVA1y, and for the impulse you will have this component. Let's put another color like this, and actually we need to write the impulse that acting by the other body, because this impulse is the impulse acting on body B, but this impulse is the impulse exerted by body B on body A, and that's what we need. So you have, here's the impulse, the integration of B dt, and this is the impulse acting by body B on body A. And finally, body A move in this direction. So body A goes in this direction and this direction. So if you get the components of mVA2, you will have mVA2x and mVA2y. This is for body A. We will do the same for body B. So for body B is the same, but it's going up. So you will have, here is mVB1x, and you will have here mVB1VB1y. And the impulse exerted by body A on body B is something like this. So you will have the integration of B dt, and the next is to, after the motion, so you will have body B is going down, so you will have mVB2x and mVB2y. So this is how the body is acting together. If we are talking about conservation of momentum, so these force, if we are talking about the whole system, not single bodies like this. So this one is a single body, like when we are dealing with A, or B separately. But if we are talking about the whole system, so we we'll have like what we did yesterday, the M A V A 1, and actually, so yeah, let's explain it from yesterday. Okay, so if I have a body here colliding with a body here, so the conservation of impulse and the conservation of a linear momentum only in y direction, because there is not any impulses in the x direction. It's only in y direction. So we will only be able to apply the conservation of linear momentum in y direction. But if our bodies are moving and colliding in this way, and we have here the integration of p dt and here the integration of p dt. So when we are talking about the system, this one will be equal to 0 because all the forces will cancel each other. So here in x direction, there is no impulse because they cancel each other if we are talking about the system. But if we are talking about single bodies, so we have this amount of impulse. So let's solve in y direction where the impulses cancel each other. So let's put here 4 in y direction. So in y direction, if we applied this equation for all the system, you will have the sum of the masses multiplied by V1 plus the sum of the integration T1, T2 of the sum of the forces dt will be equal the sum of the masses V2. So this is for the entire system. And if we are talking about entire system and we only have impulses that cancel each other like this case or this case, so this term will be equal to 0. And finally, we will have MA VA1, and it's in y direction, VA1 in y direction, because we only have impulses in y direction here, plus MB VB1 in y direction will be equal to MA VA2 in y direction plus MB VB2 in y direction. So this is the first equation after applying the conservation of linear momentum in y direction. And the direction that we have momentum in, we can apply the restitution coefficient. And restitution coefficient is only applied in the direction where we have momentum, because here in this problem we don't have momentum in we don't have impulses in x direction. The impulses are only in y direction. So these two equations are only applied in the y direction. So here we will have that VB2y minus VA2y over VA1y minus VB1y. So these two equations are representing the concept of conservation of linear momentum. So let's box them. Right, and let's get to x direction to see what we have. So there is not any impulses in x direction, and what only we have is just this and this. So all the other things are in y direction. So we will have MVA1x will be equal to MVA2x, and also similarly for body B, MVB2x will be equal to MVB2x, because there's not any impulses in x direction, so you will only have this two. So right now you will have 4 equations and you will have 4 unknowns. What are the 4 unknowns? So usually you will be given the velocity at the initial stage, like you will be given VA1 and VB2. But what you will be asked for is the VA2 and VB2. So you will be given the initial V1s for A and B, and you will be asked for the V2 for A and B. And the unknown for each one, so we have 2 unknowns for each bodies, like you will have the magnitude of the velocity and the direction of the velocity. So you will need to identify pose for A and B. And let's see for problem solving what we will be using for if we are talking about 1D impact or 2D impact. So this is 2D impact. The 1D impact is these 2 bodies are moving towards each other in both. So you only have V this way and V this way, and they contact here. This is the 1D. So let's see for problem solving what you should do. For problem solving, the only equations that we have is the conservation of linear momentum in the direction of the line of impact. So the momentum is only exists, the conservation of linear momentum is only exists in the direction of the line of impact. So let's have these actually, okay, let's write them again. VA1, and we have it in y direction, plus MB VB1 in y direction will be equal to MA VA2 in y direction plus MVB2 in y direction. This is the first equation, and y direction, actually let's write it up because we need this space. Y direction is the line of impact. And the second equation that we have, so this is 1 and 2. The second equation that we have is the restitution coefficient. So VB2y minus VA2y will over VA1y minus VB2y. And the third equation that we have is that VA1x, like this equation, will be equal to VA2x, and similarly for VB2x will be equal to VB1x, and this is the direction of the line of contact. So if we are talking about 1D impact, so this equation, you can only use this equation if we have 1D impact and there's no, actually we can remove impact. It's like 1D impulse momentum and FE is equal to 0. So if E is equal to 0, you can directly use this equation. But if you have E like this, so your problem is 1D and you have E is more than 0, so you will need to use this equation. And if you are talking about 2D impact, and E is more than 0, so you will have to use all these 4 equations. So let's apply this on an example and see how we can apply these equations. So let's have an example. So our example, let's write it actually here. So if we have like an inclined table, and this table is inclined with a triangle 4, 3, 4, 5, and you have like a soccer ball will be dropped from up there, and it starts at rest, and the mass of this ball is 0.5 kilogram. and it's going down. So here, V naught is equal to 0 because it started from rest. And then from here until it contacts a stable at this point. So let's have it like this. And actually, it will move maybe in this direction or in this direction. I don't know. It depends on the mass and the velocity and the coefficient of restitution between the pole and the surface. So we don't know actually how this pole will move. Let's assume that we have, before it contact the surface, it have V1, and just after the contact will have V2. And let's see what else. Yeah, it given that the coefficient of restitution between this pole and the surface, E is 0.75. And what is required is what is the velocity expressed V2 expressed in tangent normal. So if we are talking about tangent normal, so the normal direction will be perpendicular to the surface, like this. So this is N, and the tangent will be something like that going down. So we need this V in the tangent and normal direction. So you will get the, after you're getting the V, you get the component in the tangent and normal direction. And actually, the tangent and normal direction will help us to determine the velocities in the direction of impact, because we only have impact if we draw this here, and we have our ball here. So the ball will be exerting an impulse on the surface, and the surface will be exerting an impulse on the ball like this. So this is the direction of impact, and this is where we can apply the conservation of linear momentum. But before we do this, we need to know the velocity just before the impact. So we need to know the velocity after this body going down by 1 meter. So here we know this distance as 1 meter. Does anybody know what principles that we can use to identify the velocity at this position? Like, you given that V naught is equal to 0, and this body is at 1 meter here, and you need to get the velocity here. Does anybody know how can we get the velocity V1? We need it so we can start our linear momentum work.
Could we use the kinematics equation?
Actually, you can, but what is much more easier given velocities and given the elevations? It will be much more easier if we use the conservation of energy, but you can use kinematics. But the conservation of energy, like if we assume that this is the datum, and we just have the equation T1 plus V1 will be equal to T2 plus V2, which is this is the kinetic energy, and this is the potential energy at position 1 will be equal to the kinetic energy and potential energy at position 2. So the kinetic energy at position 1, when we mean 1, it's here, the V naught. So it will be half mv1 square, which will be 0. So actually, for not confusing you guys, let's make these nodes, and this will be 1, because this will be position node, and this will be position 1, and this will be position 2. So the V node is equal to 0. And if we have this as a datum, and we have our body is above the datum with 1 meter, so the potential energy will be mgh, and it will be m g, and h is equal to positive 1 meter. The second thing is the half m v1 square, which we don't know, we need v1, plus the potential energy at position 1. Given that this is our datum and the body will be here, so it will be at elevation 0, so it will be mg 0. So this will be equal to zeros, and finally we can cancel these m's, so you will have that v1 square will be equal to 2 multiplied by 9.81 multiplied by 1. So finally you can get v1, and it will be equal to 4.429. Four 0.429 meter per second. So if we are talking about the xy coordinate, like let's have this is x and this direction is y. So all v1 is in y direction. So if you want to put some directions, so you can have v1 will be equal 0 in the I hat plus, actually negative 4.429 in the j hat. So because the velocity is going down like this. And when we want to solve for impulse momentum, we need to analyze these velocities, one in the direction of the line of impact, and the other one is the direction of the line of contact. So we need to have like this body. This body is moving, like if this is the center, let's assume like this, v. So we need to get the component of v in this direction and the component of v in this direction, so we can apply the conservation of linear momentum in this direction. So if we need to analyze this, we need to find theta. So let's assume that this angle is theta, and it will be equal to this angle, and finally it will be equal to that angle theta. And you know that sine theta is the opposite over, so it will be 4/5 in cosine theta hypotenuse over 5. So you know sine theta and cosine theta. Just make sure that we have, okay, we have 3, 4, 5, and this angle should be equal to this angle, and this angle and this angle is 90. So this will be theta. So let's get V1 in tangent normal direction. And assuming that this is the tangent direction, so we will have V1 will be equal to, and the tangent will be positive, so it will be positive 4.429 multiplied by getting this component, it's the sine component, so it will be multiplied by sine theta 4/5, and it's in the tangent direction because tangent positive. But the cosine component is in negative n, so I put negative 4.429 multiplied by 3/5, and it's the n hat direction. So if we got these values, it will be 3.543 in the tangent direction, and you will have we need to multiply this. It will be 2.657 in the n hat direction, and all of these is meter per second, and this is meter per second. So this is in the xy direction, and this is in the tangent normal direction. And we did this so we can apply the conservation of linear momentum. So let's have here the second part of the problem, conservation of linear momentum. Okay, so for conservation of linear momentum, we will be applying these four equations, this one and this one. but we need to identify which one is y. Is it the tangent direction or is it the normal direction? So we can apply these two equations, and then we need to identify the perpendicular to the y direction, which is x, and then apply these two equations. Okay, so we know that the line of impact is in the n hat, so we can apply. Okay, let's write it here another time. So we have this, and then we have, let's make it more we have our like this, and then this is n hat, and this is where impulses acting on each other. So here's b dt, and here's b. So let's apply the, so here these two components will cancel each other, and we will only have, after we applying this equation, the sum of the masses V1 will be equal to the sum of the masses V2. So you will have that the mass 1, actually I don't know if we need to do this because it's not two bodies that contacting each other, and we can directly apply this equation. Why we do this? Because we know that this surface is not going to move. But if this body is hitting another body here and is going to move, so you will have to apply this equation. But right now we know that if we have this body is 1 and this body is 2, you definitely know that V2 is equal to 0, even before or after. So this equation will, you can apply it if you want. So, but you know that the V1 and V2 of the body, of this body, like if we, let's make it clear here. If you are saying that this surface is body B, and this surface, this body is body A, so we know VA before the contact. So we know VA1, which is here. So this is VA. And what we need is that VA2. That's what we don't know. But you know for B that VB1 equal VB2 equal to 0. So you know all of that. So you can apply actually this equation if you want, and it should give you the same one as the restitution coefficient. So you will have MA VA, and let's, yeah, it's in the n direction, VAN 1 plus MB VB N1 will be equal to MA VAN2 plus MB VBN2. And from this equation, you know that VB is equal to 0, so this will be 0 and this will be 0, and you will end up with these two terms. And also you can have this from the restitution coefficient. You can have E will be equal to, as you know, VB, and we will apply it in N, so VBN2 minus VAN2, and here we will have VAN1 minus VBN1. So this equation actually, if you want to memorize it, so these two is the one before the collision, like this one coming like VA 1, and here you have this one is VB1, and after the collision you have VB2 and VA2. So before the collision you have VA1 minus VB1, and after the collision you got VB2 is more than VA2, so we put VB2 minus VA2. So this is how you can memorize this equation. I don't know if it's in the dynamics equation sheet or not, but it's very easy to memorize it. So it's given that E is 0.75, and you know that the body B is not moving, so this will be 0, and this will be 0, and this equation will be only negative VA2 over VA1. And actually, all of these are in N direction. So AN2 and 1. So we know 0.75 multiplied by VAN1, which is this component, negative 2.657, will be equal to negative VAN2. And finally, you can get VAN2, and it will be equal to positive 1.933 meter per second. So we got the component in the normal direction for this body after the collision. So we got the normal component of this body. So let's get the other component. So the other component, we will get it from this equation. Actually, we'll give another thing. How about, yeah, we need the tangent equation. So the tangent equation, it will be like if you applied, if you have this, let's have our body like this. And this is the axes that have the normal components. And for the tangent components in this direction, it will be equal after the collision, this and this, like this equation. So MVA1 tangent will be equal to MVA2 tangent, just because in X direction, there is not like this and this. There's not any impulses to go in the equation. So you will have here that MVA1 tangent will be equal to MVA2 tangent, and we can cancel the M, and finally you will have VA tangent will be equal to VA1 tangent, which is this term, 3.543 meter per second. So right now we got VA as a tangent and normal vector, so we have 3.54 in the tangent direction plus 1.933 in the normal direction, and all of these are in meter per second. So this body will be moving, having a V normal in this direction equal to 1.933, and having another component in the tangent direction equal to 3.543, and the resultant will be something like this. So this is the resultant V. So we can get the resultant V, which will be equal to the root of 3.543 square plus 1.933 square. And this should give you 4.06 meter per second. And actually you can get the angle with the normal direction, not the X, because if we will use these two components to get theta, so theta will be equal to tan inverse. It will be, it depends on what you will divide. If you divided the tangent over the normal, like this, 3.543 over 1.933. So the angle that you will get, it's the one with the normal direction. But if you divided 1.933 over 3.543, you will get the other angles. Imagine it's something like that. And you are getting the tan theta, which is the opposite over the hypotenuse. So it will be this angle. So this is how you solve the problem. Does anybody have any question? So actually, most of the problems of the impacts, you will have to apply some kinematics first or conservation of energy to get some velocities, and you will only substitute in this for equation. You will only need this equation number 1, equation number 2, 3, and 4. Sometimes the problem is simple and you have like the one that we just solved it, that VB is equal to 0 at the position at the time 1 and time 2. But this is as simple as that. You will have to solve this for equations. Okay, does anybody have any questions on the impact or conservation of linear impulse and momentum? All right, so let's delete this or move it down. We can keep it up. All right, so just like I want to touch base on chapter 15.5. Which is the angular impulse and momentum. So we are moving to a new concept, which is the angular impulse in momentum, and we call it HO, and it's a vector quantity. So what is this quantity? So if we have this is X, Y, Z coordinate system, and we have our body is moving on this path, and let's say that our body is here, or here. And if we want to get the linear momentum of our body, we know that the momentum is equal to mv. So you will have mv like this. And the angular impulse and momentum is defined as the moment of the linear momentum of a particle about the point of interest. So if we need to get the angular momentum about point O here, so we will have to extend the direction of the linear momentum and get the perpendicular distance like this. This is the perpendicular distance d, and the scalar quantity of HO. So let's get the scalar first. Let's say here's scalar formulation. So the scalar formulation of the angular momentum HO will be equal to d, which is the perpendicular distance to the linear momentum vector multiplied by mv. So this is how you get it the angular momentum out of the linear momentum. So if we want the vector formulation of this, so HO vector will be equal to the R vector cross product by the MV vector. So we will be drawing R vector from O to our body. So this is R vector, and we have MV vector. So you multiply them, cross product, and it should give you the angular momentum of the body. So let's revise some concept how to do a cross product between two vectors. So you learn it in the high school or in the physics that you can do the cross product, something like that. Using the determinant, you have I, J, and K, and you will have the components of R, Rx, Ry, Rz, and the components of the momentum Mvx, Mvy, Mvz. So you have all of these. If you get this determinant, it should give you the vector of the linear momentum. Or you can multiply them without the determinant, just like knowing that if you have I, J, K, and if you multiply, sorry, let's make them, okay, no problem. We can keep it like this. If you multiply I by J, it should give you K. And if you multiply K by, like J by K, it will give you I, and K by I will give you J. So this is how you get it. Because let's revise this concept. So, and how we can do a cross product. So if you have, let's assume that you have, and this is R vector, and this is MV vector. So if you multiply these two vectors by each other, you can use two things to define the direction of the linear momentum. So right now, you will have the direction of the R vector, which is the first one, in the direction of your thumb. Can anybody see my hand here, or I have to hold it back, or?
Nope, we can see it. Yep.
Okay. So we can use the right-hand rule to get the direction of the linear momentum. So you have R vector and MV vector. So you curl your fingers in the direction of R towards the direction of MV vector. So you will have your thumb going down. So that means that the HO is perpendicular to both of these, and it's going down. So this is in a plane, like, let's make it, so this two, let's have this. Assume that this is a table, and you have R vector like this, and MV vector is like that, and both of them are in the same plane. So the cross product of these two should be perpendicular to each of these, and in direction using the right-hand rule. So you curl your hand using the direction starting from the first vector, which is R, and you multiply it, go towards MV, so you will find your finger is pointing down. So you know that HO is going this way. So what is if it's the reverse? So it's something like this. So you are from R, going from R to MV, it will be something like that. So this is curl is the direction of the HO, and it's going down. And this is the negative direction. So what if we have R, MV is going this way, and R is going this way, and they are in the same plane. So you will have to go from R to MV, because R is the first vector in the multiplication here. So you will go from R to MV like this. So you will curl your fingers, and you will move from R towards MV. So you will find that your finger is going up. So this is the direction of HO, and it's positive because it's going up, and this is negative because it's going down. And this is how you multiply any quantities. Like, let's assume that you are multiplying an I hat by J hat. So you will find that your fingers is going from I to J, something like that. So here's my fingers, and here's my I, and it's going in the direction of J, so it will be in the K hat direction. So if you multiply any vector in I direction, in the positive I direction, and by another vector in the J direction, so it will give you a quantity in the K hat direction. Similarly, if you multiply J by K, like going from J to K, so from J to K, it will give you a quantity in the I hat direction. So my finger is going this way. And also if you multiply K by I, so K by I will give you a quantity in the J hat direction. So let's see what will happen if we reverse this. Like, let's see what if I have, here's I, here's J, and here's K. What if I multiply J by I? So it's the reverse. So I have like 3 in the J hat direction, cross product by 2 in the I hat direction. So this will give you 2 by 3 is 6, but we don't know the direction. Is it in the positive K or in the negative K? So if you multiply J by I, so you are going from J to I. So from J to I, you will be like this. So it will be in the negative K hat direction because I'm going from J to I, not from I to J. So this will be in the negative K hat direction. Similarly, if you are multiplying K by J, you will have your finger moving from K to J. From K to J, it will be going this way, and it will be in the negative I direction. And similarly, if you are multiplying K by I, so from, I by K, so I by K, it will be something like this. So you will have your finger moving from I to K, so it will be negative J hat direction. So this is how you multiply them. And actually, you can use a different thing. So let's assume that this is I, J, K. So if you have I and multiply it by J, so you are moving your finger, so your K, the multiplication will be in this way. So if you put your fingers in the, like, let's assume that we are multiplying this R vector, and this is M V vector. So you either use your right hand rule and make it like this from R to MV, so you will have the HO in this direction. So it's perpendicular to both of these and also perpendicular to that one. Let's make it more 3D because the cross product is always in 3D, so it will be something like that. And you can use your 3 finger like this perpendicular to each other. So you will have first to have this finger in the R direction, the first one, and the second one in the V direction. So you will be getting the HO is perpendicular to them in this direction. So here's the R and here's the V, so it will be this one. So this is how you can get the cross product, and actually you will have to train yourself on how to get this. And actually in the quiz on Friday, you might be asked for about the direction of omega or the direction of the something based on the right hand rule. So you know, if you curl your hand and your finger is going outside the paper, it's a positive. But if you curl your hand and your finger is pointing inside, going down, so it will be negative. So this concept is it's general across the whole dynamic class. So just like to let you know, you should be able to know how you can apply the right hand rule so you can get the direction if it's either positive or negative. All right, so this for the the HO, so you multiply the R vector here. So I will get R vector, and here's I have MV vector. So I can extend the R vector so they can get outside from the same point. So this is the direction of R vector. And when you multiply the R vector by the MV vector, so I will go from R to MV. So it will be, my curl will be going like this. So the multiplication will be going up. So I will have my HO is going like this. In this way, HO, because I'm curling like this. So the HO is perpendicular on R and MV and is going this way. All right. So based also on this concept, we can derive what is called the moment of a force. So as you know, the moment of a force, if you have a point here and you have a force here, F, and if you want to get the moment of F about point O, you basically multiply F by distance D. So you will have the moment will be F by D. But if we want to get this in a vector quantity, so if we have these, like here's X, Y, and Z, and we have like a mass like this, and we have our particle here, and we have a sum of forces acting on this particle this way. And if we want to get the moment of all of these forces about point O, what we do is just like we draw a vector from O to the body here, and this is R vector. And finally, if we want to get the moment, the sum of all the moment about point O, so it will be the R vector cross product by the sum of F. So this is how we get the moment of a force in a vector component. So you will have, if you extend this R, it will be going this way. Here's R vector. And if you multiply the R vector by the F vector and you curl your hand moving from R to F, your finger will be pointing this way. So the moment will be something like that. So it will be, here is the sum of MO, because it will be curl like this. Because moving from R to F, it will be something like that. And here for this example, if you multiply F and getting the moment about O, so it will be something like that. So here's how does the moment look like. It will be something like that, point this way. So we can, actually the moment usually could be written as a curled arrow or a single arrow with double arrows, like this, double arrows. So you know it's going this way. But if this force is here, and you are getting like, let's say this is F1 and this is F2 and this will be M1. If you're getting M due to F2, it will be going this way and it will be something like that. M2, because it will be, the curl will be something like this and it will be going this way. So this is the direction of the moment. So you curl your hand and see what is your fingers pointing. This is positive and this is negative. So just like a brief concept to break the ice for the next lecture when we derive some formulation for the angular momentum. Does anybody have any questions? We will be continuing this concept next lecture, and we will be finishing chapter 15 next time. Does anybody have any question?
No, sir. Thank you, Professor.
Sounds good. See you next time.
See you tomorrow.
See you tomorrow.
See you tomorrow.